During the plague in the 16th century, Sir Isaac Newton studied and concluded a decent portion of optics, calculus, and the law of gravitation in his home in Worthorpe, which laid the groundwork for fundamental physics. And after many centuries, there is a theory that challenged and is proven to supersede his classical mechanics. So today we're going to talk about this theory, quantum mechanics. On Friday, April 27, 1900, the British physicist Lord Kelvin gave a speech where he claimed, "The beauty and clearness of the dynamic theory which asserts heat and light to be modes of motion is at present obscured by two clouds. One of them is the failure of Michelson Morley's experiment, and the other is black body radiation effect. Prior to the establishment of quantum mechanics, black body radiation is really a mystery for the physicists at that time. Two theories competed to explain its experimental outcome. One is corpuscular theory, represented by Wien's law, and the other is undulatory, represented by Rayleigh-James law. Unfortunately, both lacked accuracy. Under this circumstance, the rising giant Max Planck stood out. In 1894, Planck turned his attention to the problem of black body radiation. The problem focuses on the intensity of electromagnetic radiation emitted by the black body, as you can see on my hand, and its relation on the frequency of the radiation and the temperature of the body. This question has always been explored experimentally, but no theoretical treatment agreed with experimental values. Wien's law predicted the behavior at high frequencies, while Rayleigh-James law only predicted experimental values at low frequencies. Planck first proposed a solution which he called principle of elementary disorder, but this was referred to Wien-Planck law and later proven false. Later, to his frustration, he revised his approach and derived the first version of famous Planck black body radiation law. In November 1900, Planck revived his first approach, relying on Boltzmann's statistical interpretation of the second law of thermodynamics. As he later put it, "This is an act of despair. I'm ready to sacrifice any of my previous convictions about physics." The law, which is revolutionary, is now known as the Planck postulate. The electromagnetic energy could only be emitted in quantized form. In other words, the energy could only be a multiple of elementary unit, E equals h nu. Physicists now call this quanta photons, and a photon of frequency nu will always have its specific and unique energy. After the publishing of this paper, this mere purely assumption made by Planck, which is also heavily incompatible with classical mechanics, has opened a new era of physics.